Question 7. We've got a really big long question here with lots of information, but don't let that put you off, because a lot of the information here is given in the diagram. There's bits and bobs you need to be aware of, so you do need to read it carefully, but don't be put off that there's a lot of writing. It doesn't mean that you can't access the question. So let's have a look at what's going on. One end of a light inextensible string is attached to a block of mass 1.5 kilograms, so that's this. The other end of the string is attached to an object of mass 1.2 kilograms, so down here, so nothing that's not already shown in the diagram. The block is held at rest in contact with a rough plane inclined at 21 degrees to the horizontal. The string is taut and passes over a small smooth pulley at the bottom edge of the plane. So a little bit of information there then. This surface is rough, which means that friction will be involved here later on. The part of the string above the pulley is parallel to the line of greatest slope of the plane, and the object hangs freely below the pulley. That's just telling us that this string is parallel to the slope. The block is released and the object moves vertically downwards with an acceleration a meters per second. The tension in the string is T newtons. The coefficient of friction between the block and the plane is 0.8. Part 1 says show that the frictional force acting on the block has magnitude 10.98 newtons, correct to 2 decimal places. Let's add a little bit to this diagram then. We know that mu has been given, the coefficient of friction, to be 0.8. So we'll add that on up here. We'll put a little arrow on that represents our acceleration. And we know that if this block is on the slope, then there's going to be a weight downwards, which will be 1.5 g. And we know there will be a normal contact force, which is perpendicular to the slope, which we'll call R. So we've also got the friction actually. Let's put the friction on, almost forgot. Well, we know the block's moving down the slope, so limiting friction applies, and it's going to be in the opposite direction to movement, so we'll put F lim just there. So that's all the forces applied to the block. There are some forces on this which we'll probably have to consider later on in the question, but considering we're only interested in the friction, we're only bothered about these forces here. So before we can find the frictional force, we need to find the normal contact force. So we are going to start off with the 1.5 kilogram block, and we are going to resolve perpendicular to the slope. Okay, it's always a good idea in questions like this, particularly the longer, more complicated questions, to be specific about what you're doing. So we've got, let's take downwards into the slope to be the positive direction. So we've got this force of 1.5 g, and the component of that that's going into the slope is 1.5 g cos 21 degrees. I'm not going to go into detail why that is in this question. You might want to look at some simpler questions if you're not confident in this, because this question will get a bit more complicated later on. So that's the force from the component of this 1.5 g weight force into the slope. In the opposite direction, we've got the normal contact force. There are no other forces that will apply when we're going perpendicular to the slope, because these forces here, the tension in this and the F lim, in fact we should add that T on there, are parallel to the slope. And we know that the block, although it's accelerating down the slope, it's not accelerating into the slope, so mass times acceleration will give us 0 here. So our force for R is going to be 1.5 g cos 21. So let's put that into our calculator. So we've got 1.5 times 9.8 cos 21. That gives us a normal contact force of 13.7. Okay, be sure not to round at this point, at least not too much anyway, because this isn't our final answer to this part. We want to find out the value of the frictional force F lim, which is given by mu r, which is going to give us 0.8 multiplied by the normal contact force that we just found. So we'll use the value already in our calculator and just multiply it by 0.8, and we get 10.98 if we do that to 2 decimal places. So we can be fairly confident in our answer because it was a show that question and we got what it wanted us to. In question 7 part 2 it says, by applying Newton's second law to the block and to the object, find a pair of simultaneous equations in T and A. Well, we've already got all of our forces that are involved with this block here, so we'll leave that for a minute and we'll have a think about what's happening with this mass here. We've got a weight force going straight downwards of 1.2 G, and we've got a tension in the string going upwards of T. We've also got an acceleration going downwards, which is going to be the same as the acceleration up here because this string is taut, so A meters per second squared. Remember, the acceleration here and the acceleration here have the same value, and the tension either side of the pulley has the same value as well. So let's start by considering the block up here. So we've got a 1.5 kilogram block, and we are going to resolve parallel to the slope. So let's take downwards the direction of the acceleration to be positive. So we've got a force T that's down the slope. We have a component of this weight down the slope. Now remember, when we were resolving perpendicular to the slope, we did 1.5 G cos 21. Here we are going to do 1.5 G sine 21. We've also got this limiting friction in the opposite direction, so this will be negative. Let's remember what it is from here. We showed that it was 10.98 in the last part of the question. So minus 10.98. So that's our net force, and that's going to equal mass times acceleration, so 1.5 A. So this is going to be our first of the simultaneous equations. It's got T and A in it. Everything else is just a number. Let's have a look at the block. So we've got the 1.2 kilogram mass. We've already done the block, and we're going to resolve vertically. So remember, we'll take acceleration as the positive direction. We have got 1.2 G going in the positive direction, minus T because that's in the opposite direction, and that will equal mass times acceleration, so 1.2 A. So here we have a pair of simultaneous equations involving T and A. 5 marks here, not a lot written down, but we did have to do a bit of thinking because we had to put all the forces and the acceleration correctly onto our diagram. So implicitly a lot of the marks are going to be for what you've done over here. This is just the result of what you've done. Part 3 says, hence show that A equals 2.24 correct to 2 decimal places. Well, I've borrowed my 2 simultaneous equations here from the last part of the question. So we need to go ahead and solve these simultaneous equations. Considering I only want to find A, I can go ahead and eliminate T from this quite simply. All I've got to do is rearrange both of these equations to say T equals. So that just means taking all the other terms over to the other side. So I'd get T equals 1.5A plus this 10.98 minus this term here, 1.5G sine 21. A little bit easier over here. We'll take T over to that side, bring the 1.2A over here, and we would get T equals 1.2G minus 1.2A. Now that we've got 2 equations where it says T equals, we can eliminate T by setting these equal to each other. So we get 1.5A plus 10.98 minus 1.5G sine 21 equals 1.2g minus 1.2a. From here we've only got one unknown, and that's a. So let's try and isolate a, get that on its own. Let's add 1.2a to the other side. That's going to give us 2.7a. Let's bring everything else onto the other side. We get 1.2g plus 1.5g sine 21 minus 10.98. And then let's divide through. And we get a is 1.2g plus 1.5g sine 21 minus 10.98, and this whole thing will be divided by 2.7. So let's pop this into our calculator. Doing that, hopefully we should get 2.24. So I'll put a fraction in to start with. 1.2 times 9.8 plus 1.5 times 9.8 sine 21 minus, now I know the last thing I worked out was that 10.8, so I'm going to use my answer button there, and on the bottom I've just got 2.7, and magically we get 2.24, just like we expected. And that's correct to 2 decimal places. In part 4, it says, given that the object is initially 2 meters above a horizontal floor and that the block is 2.8 meters from the pulley, find the speed of the block at the instant when, and in part A, the object really reaches the floor. So what's going to happen? Remember, this is accelerating down, so this block is going to accelerate downwards, constant acceleration, for 2 meters until it hits the floor. And we want to know the speed of that block when this ball hits the floor. Now we don't need the diagram, I just think it's helpful here to visualize what's going on. So let's write down our SUVAT equation. Now if we think of our initial displacement here as 0, when it hits the floor, displacement is going to be 2 meters. The initial velocity is 0. We're trying to find the final velocity. Remember, in part 3 we showed that the acceleration is 2.24, and we don't know the time. We're not interested in the time now. So what equation have we got that involves S, U, A and V? Well, we're looking at V squared equals U squared plus 2AS. So we get V squared equals U squared is 0, so we're just going to have 2 multiplied by the acceleration, which is 2.24, multiplied by 2. So to get V, we're just going to square root all that. Let's put that into our calculator. Remember, we've got the more accurate value for the acceleration before, so we may as well use that. Square root of 2 multiplied by my answer to the last question multiplied by 2 again gives me 2.99 to 3 significant figures. For part B, we're interested in the speed when the block reaches the pulley. Well, let's not forget part A. We know that the block has moved 2 meters after part A when this particle hits the floor. So the distance it's got left to travel to reach the pulley, because that's 2.8 meters in total, is going to be 0.8 meters. We know from part 1 that the initial speed is going to be the final speed from the last part, so that's going to be 2.99 meters per second. We're trying to find V, but we're going to need to know the acceleration because it's not the same as what it is here. And the reason for that is that the forces on the block have changed now, because originally there's this tension on the block which is caused by the weight of this ball downwards. But if that ball has hit the ground, it's now on the ground, there will no longer be this tension in the rope. So I'm just going to quickly draw a new force diagram to represent the situation we've got now. So we've got our block on the slope, and we've got limiting friction is still there, and the weight is still there. And F lim, remember from before, was 10.98. And we're interested in the acceleration of this block. So, let's resolve forces down the slope. Positive direction will take us down the slope, same as before, just here, look. So we've got 1.5 G sine 21 minus the limiting friction is going to be equal to mass times acceleration, so 1.5 A. So all we've got to do to find A is 1.5 G sine 21 minus 10.98, all divided by 1.5. Let's work that out on the calculator. We've got 1.5 times 9.8 sine 21 minus 10.98, all divided by 1.5. That gives us an acceleration of negative 3.81. Now you may be thinking, why is that negative? And it's because although the block is moving down the slope, the limiting friction is actually slowing it down. Okay, so we should find when we do this calculation that the new velocity after this part is less than the velocity here. So let's put that value in for our acceleration into our SUVAT part here, minus 3.81 meters per second squared. And let's use v squared equals u squared plus 2as. So let's square root and put the numbers in one go. Well, u squared is 2.99 squared. And because this acceleration is negative, I'll put my minus sign here straight away. 2 times 3.81 times the displacement of 0.8. Let's put that into the calculator. We're going to get the square root of 2.99 squared minus 2 times 3.81 multiplied by 0.8, which gives us 1.69 to 3 significant figures. Oops. Okay, that was the last question on the paper. Thank you for watching, and I hope it's been helpful for you.